Welcome to Abstract Synthesis, where we share the stories behind interesting academic papers in the world of program synthesis and neurosymbolic AI. This podcast is brought to you by AGI Research Lab and DIA, and I'll be your host, Brian Landers. Today's guest is a Jacobs Faculty Scholar and Professor of Computer Science and Engineering at UCSD. That's the University of California, San Diego, which is where I live, so I'm very excited to speak with him today. He leads the UCSD Programming Systems Group and has published extensively on our favorite topic, program synthesis. His research group's mission is to make it easier for people to build software they can trust, which is getting more and more important as more code is generated by LLMs these days. So I couldn't be more excited to get to know him better. Welcome to the show. Can you please introduce yourself?
Yeah, hi everyone. Thanks for having me on the podcast. My name is Loris D'Antoni. As Brian said, I'm a faculty at UCSD. I've been working in program synthesis for many years, maybe 12, 13 now. And I also, before joining the University of California, San Diego, I was a faculty at the University of Wisconsin-Madison for 9 years. And besides my faculty job, I also work for a company called Code Metal. But everything I tell you today is going to be mostly about my day-to-day job as a faculty.
Excellent. That's, I think, what we want to hear about most. We've got an awesome paper to talk about, constrained adaptive rejection sampling, or CARS, and we're going to get into that. But just a little bit more on your background. I know you gave a bit of detail there, but before we dive in, tell us about how you made your way to being a professor, where you grew up. Just kind of your path through discovering this area of program synthesis.
Yeah, my path was unusual, let's say. So I grew up in Italy. I did my undergrad and my master's at the University of Torino. And there I was working on very different stuff. Initially I didn't even know I was going to do research in my life. I just met this professor called Mariangela Dezzani who taught me compilers. And during the class, she was like, "Oh, you seem very smart. Do you want to work with me?" I'm like, "Sure." I don't know. I like the class, so sounds like a plan. And I started working on this thing called type theory. And specifically, my very first paper, you will find it was about something called session types. People still work a lot on it, and I get citations for this paper. I haven't followed the field, but I heard a lot of people are excited about it. And I then started working with some folks at the University of Pennsylvania through my faculty. She introduced me to people, Benjamin Pierce and Nate Foster, who ended up being then friends and colleagues later on. And I work with them again, something related, but that I think that got me admitted at the University of Pennsylvania as a PhD student, where I then worked for 5 years with Rajiv Allure. And the funny story here is that Rajiv Allure had just gotten a grant on program synthesis. It was called the ESCAPE program, so Expedition in Computer-Aided Programming. And the goal was to make program synthesis happen. And at the time, I was like, I don't want to work on program synthesis. So I worked on automata theory for 5 years. And then as soon as I became a faculty, I was like, okay, I don't want to do automata theory anymore. So now I'm going to do program synthesis. So I was a bit of a rebellious guy, but in the end, I found the path through synthesis. And actually, the first paper I wrote on synthesis was with Rajiv, and it was about using synthesis to generate feedback for students learning computer science concepts. So the idea is that we were synthesizing actionable ways for giving basically actionable feedback for students that were trying to learn specifically automata theory. And then these ideas ended up being applied to things like teaching people programming. So if I can synthesize ways to fix your code, I can tell you what's wrong with your code and teach students some interesting stuff. But then, since I've been a faculty, I've been mostly working on generating code that does what we want and how to do that correctly in that scale. I applied program synthesis to many domains. One that was fairly successful was synthesizing network configurations so that your data centers don't go down because of something you didn't expect. We did some work on synthesizing small edits to interpretable machine learning models so that we can help people design them better. We have synthesized decoders and encoders for things, because people used to get those wrong a lot. I will I would often get these emails for myself. Dear Loris, my name has a apostrophe after the D. And there was always the still UTF encoded apostrophe. And so I was like frustrated enough that I decided to solve that problem. And I've seen many things since then. And now more recently, I had to embrace the era of AI and figure out how to do synthesis correctly with LLMs. And so that's how I got to where I am today.
What a great story. And just, you're kind of a superstar in this program synthesis space. You alongside, your colleagues at UCSD. So I feel like, you're not off the hook after this episode. I think we're going to have to do more to cover more of your papers. Maybe we could do like a live episode and interview your students and other faculty members or something at UCSD.
Sure,
so stay tuned for plans there. That's really special. I think you also have some connections to our previous podcast guest, Aus Alberguthi. Is that right too?
Yeah. So Aus and I actually met in my maybe 8th week of the PhD at the summer school in formal methods called Mark Doberdorf. It's this place, this little village in Germany where we met there. And then 2 years later, we were interns together at Microsoft Research. And then 3 years later, we were colleagues at UW-Madison for 9 years. So it's like, this is always the advice that I give to young students is like, make sure you talk to people at conferences or wherever you go, because one way or another, they hop back in your life and you will never know. So it's, Aus and I have worked together, specifically this work on early work before LLM on combining formal methods with machine learning. We were doing a lot of verification of neural networks, verification of machine learning enabled systems. And we worked together a long time, have many grants together. I think last year we graduated our last co-advised student and Anna Mayer. She's now a faculty at Carleton College. It's like, it's hard to predict what once you meet a person the first time, how then you're going to work together for 9 years.
Yeah, absolutely. And it is a small world kind of in the symbolic space or formal methods and program synthesis. So I feel like I'm starting to kind of get a sense of who's who out there. So, but there's still a lot of folks I need to get on the podcast. So that's not to say we don't have more to explore. That's super cool. And you mentioned, this, scholar role at Code Metal. So kind of, a little bit of industry work. And as you alluded to, I'm sure that, there's top secret stuff happening there as with any for-profit company. But what sort of generally attracted you to, why did you think your exact research and skills and focus were a good fit for this particular company?
Yeah, so actually before Code Metal, I was a scholar also at Amazon for 4 years, and I did a lot of fun work with great people there on applying formal methods to various domains that they care about. And then, I think a few months ago, I started getting approached by some companies that were interested in these LLMs plus verification. And I talked to several of them, and they're all doing really interesting work. And then what really attracted me with Code Metal was, well, first of all, I had been working with them I wouldn't say working, but like we had many chats. They were interested in my work, specifically what I'm going to talk today. This constraint decoding was something interesting to them. And let me tell you a little bit what they do, and then I can tell you a little bit why am I relevant to that? I don't know in the details what I can say, but essentially Code Metal places themselves in this space of how do we use LLMs to write code that does what we want, but they're not trying to solve these hard problem that some other companies are trying to solve, which is people now are going to just byte code and write code with natural language, and how do we get them to write the code they want in a way that is verifiable? And the challenge in doing that is that even if you write in English what you want, it used to be in traditional synthesis or verification that we write the code in some way, we write the specification in some other way, and then if they agree, life is good. It means we wrote the same thing twice and it matches, so probably we're right. The problem is that now if an LLM writes the code and the specification, well, it can just lie twice to make us happy. Yes. And so essentially it just can get, even though we ask something, we get a reasonable sounding answer, a specification that says, yeah, this is what I want, but it doesn't tell us the questions we didn't ask, essentially. It's like, did you think about whether your code should have this property or this other property? Should they run no matter what? Like in the example of the data center, let's say I ask an LLM, give me configurations that send traffic from A to B, from B to C, and so on. I was like, yeah, this works, it's perfect. But usually when you design that manually, you will also have things like, oh, I also want it to be fault tolerant. I also want it to be, that there are other properties that maybe you haven't stated at that point, but you might want. And so we lose that level of essentially oversight that we were having when people were doing the same thing twice and then checking them against each other. What was interesting to me is that like they don't have this problem. So what they do is that they do verified code translation. So their product that they're building is that you have code written in some language you don't like, and you want to port it into a new language you like, and or optimize it into some language you like, and you want to do that automatically with LLMs. And so here, what is interesting is that the specification is very clear. The output code should do what the input code does. There are some caveats here. People have to be careful, because what does it mean to be equivalent when you're in different languages? That you care just about the input and the output, or maybe any behavior in between needs to be equivalent, maybe should run as fast as it was running before. There are some properties you might care about. But at the high level, it's pretty clear how formal methods and formal verification can help. We just want to increase the assurance that the output is indeed equivalent to the input. And this was pretty fresh for me. It was something like I'd done a little bit of work in the past, but it was intriguing, it was interesting, and I really liked the team. As I said, they reached out to me a year ago. We were kind of collaborating research-wise. I gave a talk there. I really liked the people, and I was like, after 4 years at Amazon, I thought it was a good time to try something new. And now I've just been there for a month, but I really enjoy it, and I really like the people I'm working with. So.
That is so cool. I think a lot of what you're speaking about is sort of where we're at with, as you said, the AI era. I would say the LLM era, because, there was plenty of AI before LLMs, right? But in terms of just, code generation, how do formal methods and, languages sort of apply to this? And it's sort of like the problem of the moment. And so I really think what you have to share is super relevant. And as you said, today's paper is a great sort of entry point for that. So let's dive in. I mentioned the name of the paper is Constrained Adaptive Rejection Sampling, which everyone's got to make awesome acronyms. So you've got CARS. So I'll probably refer to it as that. I love that. Easy to remember. Someone in the YouTube comments said, like, let the, guest, like, just explain what the paper is about, like, at the highest level. So let's do that. Like, just give us kind of an overview in your own words, kind of, what is this paper about?
Yeah, so this paper came to be as it's to talk about this paper, I need to talk about the very first paper I wrote in this field, and in general, what people have been doing in this field, which is how do you get an LLM to produce outputs, sequences, like strings, that satisfy some property that you like, some constraint. And probably many of the people in the audience are familiar with this thing called constrained decoding or structured decoding. So this has come to prominence once people started building agents. They needed to get some of their outputs from the LLM to match some JSON format so that you could send it to an MCP. Basically, you could follow some MCP protocol and call some tools. And the LLMs got better and better, but some LLMs are, maybe you want to use also cheaper LLMs that are sometimes make mistakes. Or in general, the LLMs will always make some mistakes once the constraint becomes complex enough. And so what constrained or structured decoding does is that while the LLM generates the output, it essentially runs a little parser for the type of constraint you're trying to enforce, and just says, only keep tokens that will potentially lead to a sequence that satisfies the constraint. So throw away everything that for sure will violate the constraint. And this is fine. And it works. Like, people can build. It's pretty easy to build these algorithms. It's hard to make them very fast, but people have also figured out how to do that. The problem is that the analogy I give here is that now what's happening is that you don't know ahead what constraint you're going to try to satisfy. And so this is the analogy I give is that, let's say you're asking your GPS to take you to some destination, and it starts driving. And at some point, it gets halfway through, it finds that the road is closed, and you didn't know about that. And that's what constraint decoding is doing. It's like, now it has closed the road for you because that road will violate the constraint that you didn't know about. And so now you have to do a detour. And so you don't have anymore the optimal route to the destination. You suddenly are kind of fixing along the way some poor choices that you should have known from the beginning. And so this is actually what's happening when you use constrained decoding with LLM. So we had this paper at NeurIPS 2 years ago called Grammar Aligned Decoding, where we sort of formalized this problem and described it. And essentially the issue is that if you greedily follow the constraint, you are not anymore aligning with the very good distribution that the LLM learns. So the LLM is very good at generating likely sequences according to what you've asked. But now, because you're following greedily these constraints, you get not anymore necessarily the most likely sequence. You get this weird, greedy path that just keeps trying to satisfy the sequence over and over. And this can lead actually to deterioration in the quality of the output. You sometimes can get these weird programs that open many parentheses in an attempt to follow the constraints, or they just start producing outputs that are very unnatural. You will get like millions of spaces because the LLM at some point basically doesn't know what to do anymore. And that's a problem. And so essentially, it's like the issue is that like you will not know a priori whether this happens because it depends on the grammar you provide as input, on the constraint you provide as input, on your JSON schema or whatnot. Then we started this journey on figuring out how to solve this problem. So how do we get the LLM to still produce good sequences that satisfy the constraints? So right now we know how to produce sequences that satisfy the constraints, but sometimes they're not good because we are following this greedy algorithm. Going back to the GPS analogy, you can do a couple of things. So if you find a roadblock, you can decide to just now pick another road and keep going randomly and hope that eventually you reroute enough times that you get to your destination. And or there are a few other things you can do. Maybe you can drive back a little bit, add that information that now you know there is a roadblock, and try to take the next optimal route from maybe a few blocks earlier. The other thing you can do is like, maybe you didn't drive far enough, or maybe you don't care about, you really want to get the optimal route. Maybe you just drive back home, add that there is a roadblock there, and now restart driving. And then if you do this enough times, maybe you find the optimal route. And the constrained adaptive rejection sampling paper basically was this idea that is like, if I really want to find good routes, and not just somewhat good routes, the best thing you can do is basically anytime you get stuck somewhere, making a bad choice because of the constraint, getting to a roadblock, what you will do is just restart from the beginning. Now you know that there is a roadblock there. Update your basically knowledge based on that. Drive again, and if you find another roadblock, start again. And this sounds very efficient, but it turns out that if you really care about finding these very high quality routes, it's the only way you can do it. Essentially, you really need to restart every time and hope for the best. And eventually, hopefully, once you find enough knowledge, you will avoid all the roadblocks and get to the destination. So now, breaking away from the analogy for a second, so what is it, the formal problem we are trying to solve? The LLM is, in probability terms, is a sampler from a distribution. So it generates strings according to a distribution. And I have my constraint, which throws away some of these strings. And so this creates what is called a conditional distribution. Now, to sample sequences from the LLM according to the distribution, but condition on satisfying the constraints. And what CARS does, it does this algorithm where you keep finding roadblocks and restarting. The promise we do is that we do sample from this correct distribution. So this constraint distribution, this conditional distribution is actually what we are sampling with respect to. And up to this paper, the best way to do that was to just remembering these roadblocks along the way and avoiding them in future attempts. What CARS did is basically it took all this, it improved on this idea. And so the idea is that once you find enough roadblocks and you avoid them, eventually you get good samples. But how long does it take you to do that? Well, if you're unlucky and you're in situations where there is a lot of roadblocks that you can hit, it might take a long time before you discover enough that you start producing samples often enough where you don't just get stuck over and over. What CARS did is, it says, well, we know along the way, the roadblocks that we're going to hit because the GPS is telling you turn there, but you cannot turn. But while driving, we're also going to see other roadblocks that we're not going to go there because maybe we don't want to go there. But we saw that there were other roadblocks that we didn't know about. And so we're learning the extra state of the map at every step to improve how quickly we learn all the roadblocks and avoid them in future samples. Moving away from analogies, one thing we really cared about is we are using these algorithms for producing test cases for compilers. So what does this have to do? So we are using LLMs now to test compilers for languages that don't appear that much on the internet. I'm not going to go too much into detail, otherwise it's another big detour. But these languages are hard for the LLMs to generate. And so we provide these constraints, these grammars, to make sure that we get some samples in these languages. Otherwise, we are never going to produce inputs for our compilers to try. And we were observing cases where the LLM would basically get you one out of 1,000 samples are actually in this language. And that's not good. You cannot just produce 1,000 samples to produce one valid one and test. Otherwise, you never test your compiler. And so even the algorithm that remembers one roadblock, it will get to 2 out of 1,000. Like it was just, the mistakes are, there are too many mistakes to take into account that you don't make any progress. And so our new algorithm that learned from all these observable mistakes, all these observable roadblocks, after one to three bad samples, now it suddenly gets to producing 350 out of 1,000 samples are valid. So suddenly we produce, like, we have a 300x increase in utility, like meaning that with 1,000 calls before, we will only produce 1 to 2 valid samples. Now we produce 300. And so that was a big change for us. And like it allows us now to, in fact, we found a bunch of bugs in compilers because we have these algorithms that can produce a lot of test cases very quickly.
I'm going to double click on a bunch of those things because I think there's a lot to be learned within all that. And a bunch of things I learned for the first time reading this paper. Before we do those, technical details, anything we should know about, the co-authors? Who were the collaborators on this paper?
One of my co-authors is Taylor Burker-Patrick. He's a NLP's machine learning faculty here at UCSD. I've been collaborating with for the last couple of years on this topic. And one of them is Sairam Bhadia. He's a student here. He's going to start a PhD with me in fall. And he's the one that has been pushing for this compiler testing. And at the same time has been developing a lot of these ideas in this paper and running these very complicated evaluations. Nice. But the other author is an interesting story, is Pavel Paris. He's a faculty in Poland. And this goes back to talk to people, you never know where he goes. So he's a very theoretical person. Like he traditionally publishes in automata theory and logic and like very different venues. And 3 years ago, he messaged me, hey, I want to visit the US and you used to work on automata. Can I come work with you for a little bit? And just, you wanted to kind of just, get a sabbatical, I guess. And he wanted to spend a few months abroad. I say, oh, look, I'm in the middle of moving to San Diego. It's bad time. And so I was like, I didn't have the time. I was literally, it was 1 week before I was moving. I was like, I need to find a home to live in first. So maybe maybe next year. And then next year he messages like, oh, you know what? I'm going to come this year. I think I'm going to find funding through this fellowship. And I think it's going to be fun. It's like, okay. And he came and visited me. And there was a bit of impedance mismatch the first few weeks because he was speaking this language I hadn't spoken in 20 years. And I was speaking this whole new language. But he was like, I don't care. I want to learn something new. Teach me something new. And I was like, so we started working. I said, just read these papers we've been working on. And then the story is like we were trying to do a different algorithm than this. And this is why it's funny sometimes to work with people that are in different fields. In this case, a very theoretically mature person compared to me. And he goes like, oh, there is this algorithm. I mean, there is this way to do it, but it's trivial. And I'm like, what did you just say? What do you mean? Like, because he said, there is a way to solve this problem that you've been solving, but it's kind of uninteresting. It's like, yeah, but what is it? Yeah, you just do this. You just change a couple of things. Because CARS is a variant of a former algorithm we had developed. And it basically really is a line change, but it deeply affects the properties that you get from the algorithm. And I'm like, that's the paper we're going to write. So we stop everything else we were doing. And then we wrote CARS. And yeah, man.
What a cool story behind it. I had no idea anything. You read the byline and you just never know what's going on behind the scenes. But that is so cool. How special to have some, a colleague, pick you out and say, I'm going to come spend time with you, like physically relocate to where you are and hang out. That's like, it's pretty intense, but it's pretty awesome too. Actually, okay, so you brought it up, both in your past and just, kind of the paper talks about. In fact, I will say the paper was a bit intimidating to me because it has like automata theory notation like on the second page. So it starts getting very technical. But okay, so for those who haven't taken a theory course in a while or ever in my case, can you like explain briefly what automata are?
They're used for many things, but the way you learn them usually in the computer science curriculum is the simplest model of computation. So it's, imagine what computer can you build if you only have finite amount of memory? So if you only have 100 cells in your memory and they all contain just a bit. And basically, automata try to capture this idea that you only have finitely many states you can operate over. And so what can you do with that? The typical example you will hear is like, oh, maybe you can count whether the length of a string is even or odd, because I have one bit, and every time I read a new character, I change that bit. And so this only takes constant amount of computation. It takes one bit. And this is what they're called finite state automata. In this case, the two states are the bit is on or the bit is off. So now, more technically, the model of computation is described. You have states and transitions, and you have an initial state you enter from, and then you read the string one character at a time. And when you finish reading the string, you have traversed these states and transitions until you get to a final state. And if that state is a good one, you say this string, I like it. Otherwise, you say, I don't like it. Now, why is it relevant for this particular work? So automata can be used to describe strings you like and don't like. In this case, they can use to satisfy strings that satisfy a constraint versus the ones that do not satisfy a constraint. So in the example I gave you, you can imagine that you decide that if the bit at the end of the string is 0, you like the string because it means it has even length, or depending on how you build it, it has odd length. And the nice thing, one of the reasons a lot of people like automata is they have many, besides being a very simple model to study, they have a lot of nice properties that we like to exploit when building certain types of algorithms. The relation to something more people are more familiar with, many people use regular expressions in grep or in their programming language. And the efficient implementations of regular expressions usually are built by compiling these expressions to automata and then running those automata on your inputs. And then there are the other connection to this paper is like some fancier type of automata are used to build parsers to basically see if your program satisfies some syntax written in a grammar. So they appear in a lot of places in computer science, and they're sort of like the simplest model you can have, and they're very nice properties.
Very cool. Thank you for that. I got another one. Okay, so you one reading of this paper could kind of be, summary would be rejection sampling with memory, right? That's sort of the unlock. What is rejection sampling for those that don't know?
Yeah. So I guess before I really went on a detour with my map example, but so let's say you want to build, you want to use an LLM to decide to produce these MCP calls. The simplest way to do it, and that's what many people do, is that you just generate outputs. You do this until you get one that satisfies the schema you have in mind. And until you don't get the one that you like, you throw away all your samples. So I'm going to use samples here to mean one LLM output. And so it's called rejection sampling because you sample, you produce samples with a length, you produce these potentially JSON outputs until you get one that satisfies the schema. And so this is what's called rejection sampling. You reject until you get the one you like. And if you want to get more than one, you reject until you get enough that you like. The problem with rejection sampling is that you don't know a priori how long it will take you to get one that is valid. It could take you 1 sample, 10 samples, so you might never get one because it's so unlikely that you will satisfy this property. And so what our tool does is it decreases over time the chance that you will get a wrong sample. So the more we learn, the more likely it is that we will get a valid sample along the way. And really, from a mathematical perspective, let's say that you have a 10% chance of hitting the valid constraint. So this means you have a 90% chance of failing. And what CARS does is that whenever I discover a violation, and that violation has a certain probability, we are effectively subtracting the probability from that 90%. So let's say we discover that this 10% portion of the space is invalid, and it has 10% probability, 0.1. Now that 0.1 is removed, so now suddenly you are at 0.8 to 0.1. So your probability of accepting went up to 12%. Like by just throwing that away, you've thrown away a big portion of your failures. And that you're very much right, is essentially rejection samples plus memory about mistakes we made in the past.
That is so cool. I mean, seems obviously way more efficient. I think, okay, here's a question about, people might look at this and think, okay, if I can generate valid outputs, like, why should I care whether the distribution is exactly right? So why do you think that preserving the model's original distribution, that's kind of the whole point of cars, like, why is that important? And specifically in applications like you mentioned in the paper, I think there was like fuzzing, code generation, and really cool like science stuff like molecular generation. Why for those applications does this matter for preserving the model's original distribution?
Yeah, so there are two answers. So one is like often people say, but look, at the end of the day, all you care about is getting a sample that works. But usually the constraints that people use in constraining the LLM, they're not the full answer. It's like here is like the sequence is valid syntax, let's say it's valid in some grammar. That doesn't mean it's the correct program, is the one you wanted. So you still want the best programs that satisfy the syntax in the hope that you will be the correct one. So that's kind of the first part of the answer. But you're very much right that in the paper, we mostly focus in the case where you want to produce not just one sample, but many samples, and ideally that they're well distributed. So in the case of fuzzing, that's a very good setting where, what is fuzzing? Fuzzing is this program testing where you want to generate a lot of random inputs, and hopefully those inputs cover different parts of the system you're trying to test. So if you just get inputs that test 10 lines of code out of your 1,000, those are, and you get 50 tests like that, yeah, that's not very useful. Like what you want is ideally that the inputs you receive are interesting and diverse. And we have evidence that from a previous paper that the LLM is good, in fact, at generating diverse inputs. But once you put these constraints and you distort distribution, suddenly you are basically hurting its ability to generate diverse inputs because it gets stuck into following the constraint and generating unnatural inputs for you. And so their diversity is very important. And in cars, you will find this table where this evaluation on fuzzing that shows really that the closer you get to this true distribution, the more bugs let's say the more coverage you will get in the system you're testing. And from other papers, we have evidence also that you find more bugs, in fact, when you do it this way. So the more your inputs are spread out, and the LLM is good at that, the more you're going to find interesting behaviors. The other application you mentioned is like, I guess this is, in anything where you want to do some kind of knowledge discovery, it's like you don't care about getting one particular output from the LLM. You want to get a lot of possibilities to explore to then see if they're interesting for anything. And so this generating molecules is another example. People are trying to do this drug discovery. In other cases, like now people are trying to generate interesting mathematical conjectures. And so you can imagine that maybe you're constraining your output to be valid syntax in a theorem prover like clean. But if you get the same conjecture over and over, that's not interesting. So you still want to have some kind of diversity.
This makes sense. Okay, I totally get it. There's a bit of a, thing here where it sounds like cars is like perfect, like you get the best of both worlds. You've got the improved efficiency, you preserve the exact constrained distribution from the original model. Are there any limitations like, in this approach? And sort of, where do you go next with it? Where can you kind of take the next leap with cars?
I mean, one thing is that you might not always care about having the perfect distribution because maybe you're not willing to waste an unbounded number of samples before getting a good one. And so we have other algorithms that are more hybrid, sort of like their best effort. They're trying, along the way, they try to learn this distribution, but maybe initially they will produce some samples that are not very well distributed, but it will still keep giving you samples. And those essentially are the variants I was mentioning before of getting stuck at you find a block in the road. Maybe you don't need to drive all the way home. Just drive 2 blocks back and try again. So there are variants that do kind of these other approaches. And they trade-offs. Like you will get more sample efficiency, meaning you waste fewer samples, you don't reject samples, but maybe your distribution can be funky and take a long time to get to the right one. But in some applications, that's fine. One thing we're really excited about now, well, there are 2 things we're excited about. But we have many things we're excited about. I'm going to tell you 3, actually. One is we just published a paper at ICML where now we do this for diffusion models. And so I think in diffusion models, really, there is a whole new spectrum of possibilities that are open, and a whole new set of challenges. And so now we have essentially a cars. It's not cars, actually. It's better than cars. It's this problem with the distortion we show you can be avoided completely by just computing the gradient of the model towards the constraint satisfaction. And so that's one thing we're excited about. One pragmatic problem we're interested in is who gives you these constraints? So for the MCP and JSON schema, okay, we got it. You can write your JSON schema. But in many practical applications, people always ask me, yeah, but who gives you these constraints? What are you gonna actually, what problems are you going to solve that requires adding these constraints? And if you need to write the constraints by hand, you might as well just generate some synthetic data to get the LLM to not make the mistakes in the first place.
Yeah.
And that's a valid point. And so now we have this work that we just put up on Archive where we can actually learn these constraints by just, if you have a checker in the sense of, like in our case, let's say you have a type checker or a parser or something that can tell you this program is bad or not bad, we can actually try to then use LLMs themselves to learn constraints for future interactions. And we show that this works really well. Like you can get a very good LLM to teach the small LLM how to avoid problems and basically teach them the constraints so that it avoids future mistakes. But you don't need to start with the constraint at all. You learn it along the way. And this is very related to program synthesis. In program synthesis, this will be called, there are various nameplates, but like constraint. In SAT solvers, this is called CDCL, conflict-driven closed learning. In program synthesis, these ideas have appeared in the past, and now we're just pushing them to LLMs. And the last thing I want to mention is not all constraints are valid, invalid. Sometimes constraints are like, I like this more than I like this. You want to say something like, oh, I have another model, and that model is very good at predicting maybe whether this protein will fold, or whether this particular molecule is synthesizable, or whether this program will cause some trouble along the way. And now, what if you want to still produce samples from within an LLM according to these quantitative constraints? I now want to combine essentially one applications we have. You have two LLMs, and one is very good at one thing, one is very good at something else, and I want to get their product. But maybe sometimes I don't want their product. Maybe sometimes I want the majority vote. Maybe sometimes I want A minus B, or I want the biggest disagreement. And so now we're trying to take these ideas and extend them to this setting where you can program with multiple LLMs and be like, I want, give me the output on which this expert agrees, this expert disagrees, and these two other experts together come up with a common conclusion. And how do we build samplers for that? And so that's also very exciting.
All right. Wow. This is quite the slate of papers coming up here.
Hopefully.
Well, I mean, some of it sounds like it's already happening and submitted and everything, but I love that. I love that you found something that like is so interesting that you can kind of create multiple research threads out of it. That's super cool. One thing that occurs to me, and you have a colleague, Nadia Polikarpova, who's also a total, in my opinion, badass in the program synthesis world. Here you are, world-class symbolic AI experts. And now here comes the LLM era. Everyone's scaling everything, and you get these great results from LLMs, and we're in agentic code gen and all this stuff. How has your, work and focus and maybe your students' work changed throughout this kind of introduction of this era?
I would say these are hard times. And I think they're hard and easy times. It's definitely we need to reinvent ourselves and quickly. But the good news is that we have especially people who have done formal methods or programming languages work, I think they have very solid background to build on. And we like to think, this is like what people in PL think, in programming languages think about. We think we have good taste. And I think taste is going to come a long way now in designing sort of the next generation of programming systems that help programmers do what they want. And that was always our mission, essentially. Programming languages researchers, ultimately, they always say our goal is to help people write code that does what they want. And now there is this new ability to generate a lot of stuff at scale, but it's pretty wild. Like it's unregulated. It's like we live in the anarchy of code, essentially. And how do we put some rules around that, and how do we help people follow those rules? So you mentioned Nadia. We have this project now with Nadia. We also put this paper on archive, and I also saw that many other labs have been doing some similar ideas, where essentially it's like, look, we have 50 years of research on how to write code that does what we want. We have type systems, we have program verifiers, we have theorem provers. So what if we just forced agents or whatever generates code to just generate code in languages where we can give promises to the users? So for example, if your code type checks, it will never be, if the code generated by your agent type checks in this language, you will never have a prompt injection, just because by definition, this program cannot be susceptible to prompt injection.
That's awesome.
And,
yeah, super valuable.
and it sounds incredible, but at the end of the day, these are problems we've solved before. We had SQL injections before prompt injections, and they were not a very different problem. We solved them by basically preventing what can flow into certain parts of your code. And now we're kind of reinventing the wheel. And the challenge is partly to design something good, something ergonomic that people will actually use. That's a challenge. But also to do it faster than the 50 bad solutions that are coming that are just hacks. And so that's always the issue, right? It's like, people build something fast because they need it, but then sometimes we regret those decisions later on.
Yeah, and these problems that you described, that formal methods and program synthesis can help with, I feel like your phone's going to be ringing off the hook now, because prompt injection, this kind of thing, these are big problems for people. So I think it's going to be really encouraging, to the corporations and even the big labs that like this symbolic work can kind of come to the rescue with a lot of those edge cases and issues. I love that confidence. So very cool there.
And you asked me how the students feel about it. I think in general, some are more worried than others, and some are good at kind of adapting better than others. And part of my role as an advisor is sort of making sure that they get to the best possible outcome, whatever it is that they want to do. And some people, not everybody wants to work necessarily on this stuff, and that's okay. We can just always find, like, that's always been a PhD. Like, not everybody that starts a PhD is going to work on the hottest thing, and they shouldn't. In fact, I think if your motivation for working on this is just because it's hot, you definitely should not. The goal should be that you work on whatever usually people say you have to work on something that you're naturally somewhat good at. You find interesting enough that you actually can keep working on it. And the idea, you have to find a number of problems that keep you awake at night. That's sort of when you get into the excitement mode. And so what I've been doing is just kind of like my lab has been now riding a little bit of this momentum. Is like, there is once enough critical mass comes to these papers, people get excited about wanting to be part of it. But some people also be like, this particular problem doesn't appeal to me. I have some students that are still doing some traditional synthesis stuff, and they're like, I really like this. I think it's very clean. I can understand it. And you can still have a lot of value out of solving problems in a different way. So it's still very exciting.
This sounds like being a parent or something, where you can kind of guide people, but you can't sort of decide for them, like where their passions will surface,
Yeah.
But you probably have a lot more influence than you think. And it sounds like you're guiding the team, very well. They're in good hands, I think.
Thanks.
And program synthesis is the focus of the show. Where do you see, exciting opportunities beyond the ones that we've, spoken about already with cars and this kind of, language migration kind of opportunities? What comes to mind for promising threads that researchers can work on?
Yeah, I think there's also piggyback, since you mentioned Nadia. This is something she's working on, but I think if you look online, there has been a lot of worries recently about the problem I started the whole conversation with. We used to be like, you decide first what you want to write, and then you try to write it. And now instead, you first write, and then you decide what you wanted to write. And I think that's an opportunity for synthesis on basically externalizing intent. So when people use LLMs to write code, how can we recover some information about what they have written? Like, if synthesizing instead of the code specifications that describe in a human-readable yet formal way what the code you generated does. And I think you will hear a lot these words. Some of the funding agencies like to say scalable oversight. How do I program 10,000 lines of code and still be pretty convinced that I know what the code is doing? And I think that's an interesting problem. So Nadia, for example, is working on it from an HCI perspective. It's just like, how do I even communicate to users what it is that they're trying to do, and how do they generate these formulas in a way that I actually can check that they are valid, like these properties that they capture some specification, but how do I check that they're valid? But how do I communicate them to the user in a way that is useful? And what information is useful? Is knowing that this variable is always positive useful? Probably not. Is knowing that if you trigger a transaction for your bank account and is accepted, you get your money? Probably that's a useful specification you care about.
Yes.
I think a lot of interest will go in the next couple of years from our community will move towards like, how do we regain this oversight? Like, how do we get back something that convinces us that our code is indeed correct? And so it's a bit backwards because it's the opposite of what it used to be. And I did this, some of my students actually, they did some work in this. We had a couple of works called Loud last year at Uppsala, and Spyro a couple of years before, where we were using traditional synthesis, synthesizing properties out of code. But now there is really an opportunity of figuring out how to do it at scale and really help people basically regain control over their code.
I love that. What a pitch, man. Regain control over the wild west of code gen. It's really cool. And I think the work you all done is amazing. And I'm so excited to keep chatting with you about, where you all go, and maybe feature, like I said, some of your students. Love to have Nadia on as well. Put in a good word for me. Before I let you go, anything you want to call attention to, other papers to check out? Are you looking for students, as an advisor, for PhD students? What's on your mind?
Yeah, I always say I'm always looking for students. I realized last year I might have maxed out, but I'm always looking for students. Always apply. And
good problem.
And I always say next year I'm not going to hire students, and then I always hire too. So it's in practice. Yeah, you should look what my students are doing. The most relevant one, I guess, Jim Kim, one of that is doing a lot of the work I described, is going to be in the job market next year. So get in before someone else does.
Nice.
Maybe he will be your next podcast speaker, because there's a lot of things to say.
Let's get him on.
But yeah, it's. I think it's a fun time. I think he's like. I understand. Like in the last 2 years, there was this gut reaction from a lot of people that like there is uncertainty and fear in a lot of the things you're doing. But it's also true that now it's a good time to be a researcher. If you have a lot of ideas, now you can prototype them quickly and do a lot of things that we weren't able to do before. So I hope that people figure out a way to maximize their creativity and ideas, rather than being worried more about what they cannot do anymore. And I was kind of stuck in a little bit in that spot when I moved to some of these LLM work, because it was like everything I've done now is one GPT call away, and how do you get out of there? But then you realize that it's not true. It's just like when you build strong foundations, then it's pretty easy to adapt. And so I think that's what the symbolic world has been doing. It still survives because fundamentally the ideas keep coming over and over, just in different forms. Versus the hacky stuff and the quick papers that people put out sometimes just to be the first, those usually they don't last as long. So I think if you're doing deep work, you're going to be fine. That's kind of my message.
I could not agree more. That is exactly aligned with our, thesis at India. Everyone, listen to Loris's advice here. I think he's absolutely correct. Plenty of work for, folks to apply symbolic work to LLMs, to its own sort of theory, applications. There's just a whole world to be discovered. And a lot of what kind of, led to sort of a plateau, like within the symbolic world previously, is unlocking. And so you could be the one to discover that. So thank you, Loris. Again, I want to keep collaborating with you. Really glad to make your acquaintance here in San Diego and finally infiltrate the program synthesis crew at UCSD. Yeah. But I really appreciate your time, and thank you so much for joining us.
Yeah, thanks for having me.
All right, everybody. Hope to see you next time. Want to hear from you. If you have any ideas for future guests or critique or comments about the show, leave a comment in YouTube. You can find us. We're online. We're on Twitter as well. So hope to see you again on the next episode of Abstract Synthesis.